Okay, if you allow me, because I cannot do it. Okay, make it now. Is it visible?
Yes, it is visible.
Okay, good.
Yes, yeah, perfect. So should we start, Sandeep? Sandeep?
Yes, we can start now. I think we are already 2 minutes over. We can start.
All right, so welcome everyone to this session of today. So today we have two talks and then a poster session in this in this afternoon session. Our first talk is by Professor Sorin Paranov. Sorin Paranov has studied physics as an undergraduate student at University of Bucharest. He then went on to University of Illinois at Urbana-Champaign to pursue a PhD in theoretical physics on ultra-cold degenerate quantum gases. He, he worked at the University of Jablonska as a postdoc and senior researcher, after which he moved to Aalto University in Helsinki. At Aalto, he is leading an experimental group doing research in superconducting circuits. So I would like to welcome him on this conference. Yeah, Professor Parab.
Thanks a lot, and thanks for the invitation. And good morning, good afternoon, whatever applies to everybody. And nice for being here. So I will talk about some experiments and some theory that has been done in my group already for some time now, related to three-level systems. So the topic is stimulated Raman adiabatic processes in superconducting qubits, and the focus of this talk is the Majorana representation of this process. This is based on this paper, which was published this year in PhysRef Research. And Shruti, Dogra, Antideb Salainen have contributed this paper. And the summary of this talk is the following. So I will say a few words about adiabatic and superadiabatic processes. Then I will start to discuss the Majorana representation. What does it mean? How can it be introduced? What are spin coherent states? What is the angular momentum that one could introduce associated with a three-level system? And then the two-qubit representation that can be attached to this three-level system as well. And then we'll start to look at processes like stirrup and sus-stirrup. So we want to understand and realize or have a geometric representation of these processes. So both for pure and mixed qubit states, the mixed case being very relevant for experiments because, of course, the states in the experiment are mixed typically. And then some words about process tomography that can be attempted in this qubit system and how would it look like, and then a few words of conclusions. So these adiabatic and superadiabatic processes have been pursued theoretically by a number of researchers. So they have been first introduced in these papers by Demir, Plak, and Rice, and by Berry. But of course, there is also other work that has been done complementary to these ones. So especially a very clear picture of qubits has been done in this paper from 2014. And then we have also been doing quite a lot of work and trying to understand, for instance, how these superadiabatic processes can be used to realize gates, not only transfer of population. And then we did some experiments which were published this year and the previous year in these journals, and more or less what I will say about the theoretical part is motivated by these experiments, which I will, some of the results from these experiments I will show you briefly in the next slides. So I will start with stir-up. What does it mean, and how can we understand it? So when you have three-level systems, everything that I will say is about three-level system. That should be very clear from the beginning. So we have a system where the levels are 0, 1, and 2. It's that simple. But there's a lot of physics that can be unearthed from this three-level system. And so if we have a Hamiltonian that drives the qubit, one possibility is to drive the transitions between the states 0 and 1, so the 0-1 transition, with some kind of Rabi frequency omega 0-1. And then we can also drive the transition between the states 1 and 2, like here, with some Rabi frequency 1-2, omega 1-2. And so there could be also detunings in principle, like delta 0-1, the detuning between this coupling field and the 0-1 transition, and delta 1-2 would be the corresponding detuning between the 1-2 field and the 1-2 transition. But now what is interesting in this system is that if you look at this Hamiltonian, it looks, okay, what can be so interesting about it? It's just a 3x3 matrix. But if you diagonalize it, you will discover that there is a state, there's an eigenstate, which is called the dark state. And this eigenstate has the following very simple expression. So it's a cosine of theta minus sine of theta, each of them multiplied by the ground state and by the second excited state. So what we find, and the other two eigenvalues are these plus and minus. So these are combinations in general of all the three states, 0, 1, and 2. So these are the three eigenstates. And what is interesting is that you see, if you look at this dark state, it doesn't contain the first excited state. It's just a combination of 0 and 2 state. So whatever happens with the first excited state, it's irrelevant. It's not seen by this dark state. And in some sense, for instance, this first excited state can be also highly decaying, and this will not be reflected at all in the expression of this of the dynamics of the Hamiltonian if it's confined to this dark state, which will happen, as you will see soon, in the case of stirrup. And then we can also, yeah, I didn't say that these thetas that are written here have this expression, so cosine of theta and sine of theta can be written as a function of this couplings omegas. Okay, and there is also this angle phi here that has this kind of expression, but this we will not use that much in the what follows. The point is that there is this mixing angle theta, which combines the states 0 and 2, and they have these expressions. And from this expression, you can see that they depend on the omegas. And these omegas is something that we can control experimentally. So we can really tune these omegas, make them time dependent, do whatever we wish to do with them, and then control the angles theta here. And if we do so, we can realize a dynamics which is adiabatic, in the sense that we start with a Hamiltonian in the ground state, in this state 0. So that would correspond to this angle theta being 0. So we start here, and then we slowly crank up these omegas in such a way that instead of the state 0, at the end of the process, we will end up in state 2. And so this means that at the end of the process, this theta here will be pi over 2. So we end up with we start with the state 0, and we end up with the state -2 to be strict, yeah? So this is what we plan to do. We want to do these things adiabatically and keep the Hamiltonian in this dark state, which is written here all the time. So this means that we have to be slow. If we are too fast, then we will break the adiabaticity condition, and we will start to excite the states plus and minus, which are written here. Now, this adiabaticity condition can be written explicitly like this here, so which has a very clear physical meaning that this probability of the transitions from the dark states to the plus and minus states, they have to be much smaller than the difference between the frequencies. And if you do this calculation in a thorough way, you will find out that there is also a so-called global adiabaticity condition, which allows us to express this condition in a much simpler way based on this omega, which is the amplitude, one of these amplitudes, and the sigma, which is the width of these pulses that we put here that would turn out to be Gaussian. Okay, so this is the physics or this is the theoretical part. And then we would like to ask also the question, so this has been known because stirrup is a known process and we have also done it experimentally. But the next step here is that can we do this faster than adiabatic? By in some way, can we overcome this adiabaticity condition, make this process faster? Because the problem that we have in the experiment is that these qubits or qubits are, of course, not perfect devices. They decay, they have a finite lifetime. So we would like to speed up this process. All right, so what can be done here? So we have the Hamiltonian that we wrote before. So it's same as before, but with some phases this time that reflect the fact that these omegas, there will be microwave fields, they will have some phases, and there's going to be couplings here, 0, 1, and 1, 2, precisely like in that Hamiltonian. So this H0 is the stirrup Hamiltonian that you have seen before. And now what can be shown is that you can introduce a so-called counter adiabatic or counter drive Hamiltonian, which is written in this form. So this counter adiabatic Hamiltonian turns out to be, for a three-level system, of a very peculiar form. So it should couple the state 0 and 2. So it will have elements in this kind of places here. So in general, I can write it with some phase here and with some omega here, but it turns out that for this condition of canceling the non-adiabatic excitations in the system to hold, you must have this type of very specific form. So this omega 0, 2 should be given by exactly twice this theta dot here. And there should be also a phase, which you can see here in this I that appears here. So it's an interesting thing. So you see before in the previous slide, we had these omegas here written in such a way that the phases were completely irrelevant. But now the phases will play a very critical role here. There should be this kind of complex phase that we have to somehow control and put externally in the system, and also this amplitude is a very specific form as shown here. If you write this total Hamiltonian, you can soon realize that you need the Gell-Mann matrices representation because these are 3x3 matrices, and the Gell-Mann representation is an appropriate basis for this Hamiltonians to expand in. So they look like this, with where these lambdas are combinations of symmetric and anti-symmetric Gell-Mann matrices. All right. Now, what has been done in the experiment that I will briefly mention is that we indeed put this omega 0, 1 here as one of the couplings. We have another one omega 1, 2 here. And the way in which we realize the third coupling element between 0 and 2 is that we put a 2-photon transition that couples these two states and doesn't transfer any population of this intermediate state. So to recall, one important feature of stirrup is that when you do only this coupling, omega 0 and omega 2, things are done in such a way that this state 1 is never populated. So all the dynamics happens in the subspace of spanned by the state 0 and by the state 2, and nothing goes on the state 1. Similarly here, if we add this coupling between this two-photon coupling, by the existence of this detuning delta, we will not have population on the state 1. So the process that we aim at is something that keeps the state 1 with 0 population. The pulses look like this, so they have to be engineered in such a way that they act in time domain in a specific order, which is called a counterintuitive order, as Shruti was mentioning also yesterday. So the first pulse that goes is the 1 to 2 pulse. This guy is put first, and then this guy is put first to realize the stirrup. And then this counter diabatic pulse, which is the red one here, is somehow in between them. It acts exactly in the region of maximum transfer between these two stirrup pulses. Now, what can be shown here is something very interesting, is that these 3 pulses, they have phases, of course, and these are the phases that we can attach to them. Yeah, 0, 1, 1, 2, and 2, 0. And if you look at this figure, these phases sum up in a certain order to produce this total phase phi, which is a gauge invariant phase. So this is pretty much like in the Aharonov-Bohm effect physics, where there is a gauge invariant phase. If you think about these states 0, 1, and 2, you can imagine them as being really positions in a lattice, in a triangular lattice. And this will be the phase corresponding to, if you want, a magnetic field that you put in this kind of configuration in this plaquette. So this is very important because it really allows us to control the entire dynamics of the system by phases, by controlling this total phase here through either one of these phases that appear in this circle. So what do we see in the experiment? We see the following thing, that for the case of stirrup, which you see here in this figure, there is indeed a population transfer which we can do up to some 0.8 something in this particular sample, and it agrees with the simulation pretty well, I would say. But when we crank up the supradiabatic stirrup, this stirrup, we can see that the population increases to quite high values, above 0.9. So there's a clear difference between them, and it's exactly the difference predicted by the theory. And it shows that this supradiabatic process is indeed a viable option for a 3-level system. All right, so these are the experiment. This is the experiment, and that shows the supradiabatic process. And then we also checked what I have said before about the phase, because this is very interesting. So indeed, you have this gauge invariant phase phi, and it's the sum of these phases that we put in the system. Or we can change these phases as well to get the same phase. And what you see here plotted in this kind of cube is the following thing, is the fact that if you look at these lines here, they are like triangles, yeah? So you can see that, you can imagine that they are like some planes that intersect this axis, right, at some angle. So this, like this kind of triangle will form a plane, if you imagine in 3 dimensions, that intersect these 3 axes at some points here. And if you think about the equation of a plane, you realize that it's exactly this kind of combination of phases that you see here. So what is plotted here are the phases phi 1, 2, phi 0, 1. And actually on this axis is not the phase phi 2, 0, but it's the phase of each of these each of the photons that create these 2-photon pulses. So you also might notice that the periodicity along this axis, therefore, is going to be different from the periodicity of this axis by a factor of 2. And this is because when you put a 2-photon pulse, actually you have to double the phase of this of each of these fields that create a 2-photon pulse. So the equation of this plane is in fact the one written here when you take into account the 2-photon phase. So it's exactly this thing which is represented as planes here. Okay, and now in order to have the superadiabaticity condition, I was telling you before that the phases have to be arranged in a very peculiar way. And this condition is this one, that the phase is the sum of the phases in this order is minus pi over 2. And this is realized on these bright lines here. In fact, this corresponds to the condition that you see here. And also the omega 02, it has to be twice theta dot, twice the mixing angle, the variation of the mixing angle in the time domain. So overall, to remind you, we have now this Hamiltonian, so omega 01, 01 plus omega 12, 12, and then this coupling 02 with some phase, overall phase, or gauge invariant phase phi. So this phase again is a synthetic, effectively a synthetic phase that we can create by external means in our system, by just arranging the phases of our generators. Okay, we can also do something more in detail, namely to look what happens in the parameter space with these processes. So what you see here, these two plots, these two upper plots, they correspond to stirrup. This is experiment and this is theory. And the lower plots, they correspond to superadiabatic stirrup. Again, this is experiment on the left, and on the right, it's theory. So what has been done here is that we explore these two processes in the parameter space. Sigma is the width of the Gaussians that we put here, and Ts is the separation time between them. And what is seen here is that stirrup doesn't work for some parameters. It works for other parameters, but in this region it doesn't work, as predicted also by theory. And the reason for this is that the adiabaticity condition is broken. But stirrup, superadiabatic stirrup, fixes this problem. So you see that this picture is basically flat, nothing fancy happens. There is transfer of population to very high, large values, even in this region where stirrup doesn't work. Yeah, so this is the result here. And we can introduce a so-called quantum speed limit, which can be defined by the probabilities of transferring from the state 0 to, by the overlap of state, how much is transferred on the state from the state 0 to state 2. And in the case of the stirrup, this we can drive this process by, you see, by this kind of numbers, which are nanoseconds, like 55 nanoseconds, 45 nanoseconds. But in the case of superadiabatic stirrup, we can really make things faster, like about 15 nanoseconds, and the process would still be working. Now, what we have been struggling with is to find some kind of nice geometric representation for these three-level systems. Because the thing is that we have, for the two-level system, of course, we have the block representation, which allows us to visualize quite nicely what happens on with the state on the block sphere. But for the case of three-level system, it's not that simple. And what we have been lucky with is the existence of this Majorana paper from 1932. So this has been, in fact, known by Majorana, how to do this kind of representation. And we looked into it and tried to adapt what has been done there for the particular case of a three-level system. But in general, the representation works like this. So you have a state psi, which you can expand in the basis of the angular momentum. In general, if you have some kind of angular momentum, Jm, the standard basis. You can expand it like this. And then you can introduce a so-called spin coherent state, which is defined like this, pretty much in analogy with how you would define a coherent state in quantum optics with operation and annihilation operators A and A dagger, which are replaced by J minus and J plus here. So this is pretty much the equivalent of that. And then instead of looking at projections of on the state Gm, you take your state and you project it on the state J minus N. Yeah, here it's the same state here, different notation, unfortunately. And yeah, and then you realize that if you do this kind of projection, you can write things in this way with this kind of polynomial that appears naturally, I would say. This is the so-called Majorana polynomial. And this variable zeta is defined as tangent of theta over 2 eta I phi. And you will see next that it's related to the stereographic projection of the sphere. So this polynomial is effectively defined in this way. So its powers is just a polynomial in terms of this zeta. Its powers of this type of form with coefficients given by this expression where the C is the C that you see here. Okay, so this is what Majorana has done. And he has done this, in fact, in this old paper in 1932 in a very brief way. So he introduced exactly this polynomial that I mentioned before. We, in fact, are using exactly the same notations to keep to be historically accurate, let's say. So he has introduced this polynomial, but without much derivation of it. So he says that it's obvious for him. Senza difficoltà is without any difficulty in Italia. Yeah, it can be verified. It says without difficulty that this representation, geometrical representation, does not depend on the system of coordinates. All right, so that's true, but that's pretty much over. There is no further derivation of why is it so. But now we know, of course, we know everything about this representation, and we can use it. And how it works. So in this representation, we can all the operators become polynomials, and they acquire differential polynomials, in fact, of this form. You can see it for the angular momentum, for example. So the angular momentum is Jx, Jy, Jz on the three axes, and each of these x, y, z components, they have this. They can be shown that they have the following expression in terms of the zeta. So it's interesting. You see, operators become this kind of differential polynomials, and the states. You will see what kind of representation they acquire. Now, there is also an interesting detour of the story, namely that if you take a Q-trig state, for instance, you can also represent it as a symmetrized 2-qubit state. So you start to wonder what is the connection between the qubits that appear here in this representation and the Majorana representation. And yeah, so this kind of psi, small psi that appear here, you can write it pretty much like this on the block sphere with this kind of standard representation as a cosine of theta and sine over theta in some phase here. And you can define a concurrence as well of this state. And it turns out that it will have this kind of expression depending on the angle eta that you see here. And this angle turns out to be the angle between the so-called Majorana stars. Maybe I should tell the story a bit in a different way. So now that we have this polynomial here, you see it's a function of this zeta, we can ask ourselves what are the zeros of this polynomial. And the zeros of this polynomial will be the so-called Majorana stars, which we can represent on a sphere by using this kind of representation itself of an angle theta and phi. And for Q treat, which has 3 levels, there will be 2 stars. So we have a representation in which there are 2 Majorana stars on a sphere, and there's an angle eta between them. This is this angle here. So this star 1 and star 2 are the Majorana stars. And so we can calculate the concurrence here, and we can find a nice expression in terms of the angle between the Majorana stars. So this nicely connects now these 2 representations here. Also for mixed states, we use this kind of representation, which is kind of standard here, and we find that this parameter r is again related to the Majorana stars vectors S1 and S2 in this way. So this establishes a very nice connection between the 2 representations of, again, the representation of the Majorana 2 stars for the Q treat and this symmetrized 2-qubit state. Now, I mentioned before the angular momentum. This angular momentum also has a nice geometric representation. So first of all, the average of the angular momentum is this R that I mentioned before, which is related to the mixedness of the state. The average of the angular momentum can be written in this form. We can show this like the sum of these 2 vectors here and normalized by this factor. And the modulus of this average of J takes this form in terms of the eta angle, of the angle between the 2 Majorana stars. So this is getting a bit more abstract now, but we want soon to get back to the experiment and see what, in which way it helps us and how we can represent stuff by this procedure. So just to remind you that in the case of the stirrup, in the case of the ideal stirrup, as I mentioned before, we have the following things. We have pulses here that are of this kind of shape. The omega 1, 2 pulse goes first, and the omega 0, 1 goes second. And the mixing angle varies from 0 to pi over 2. And then we also have, we can plot the population as it's getting transferred from the state 0 to the state 2 in this plot here. So you see the population of state 2 increases. Here the pulses start to act, and it increases close to a large value. And in the Majorana representation, now this looks like this. There are 2 stars here, which are plotted here. And we start with these 2 stars in this position here at the North Pole. And then as the time goes by, they evolve like this and like this towards the South Pole. And what is interesting is that now we can really visualize what happens in this representation. So we have the dark state, which is cosine of theta 0 minus sine theta of times 2. And this dark state, we can write it as a polynomial now. In the Majorana representation, it will look like this. So it's a polynomial in terms of this zeta, and it's cosine of theta zeta squared minus sine of theta. So it's a second order polynomial, and the solutions of this polynomial, when solved, give exactly these points here, which are the Majorana stars. All right, things then start to look like this for different processes that we have here. For the case of the stirrup, we can see that these Majorana stars, they evolve like this on the Bloch sphere. So you see the process is not perfect. It has all kinds of kinks that you can see here. And these are due to the fact that this process is not infinitely slow. And the angular momentum will be represented by the black line here all the time. And we started to understand and analyze how this goes. So for instance, the population on the state 1, which is plotted here with this continuous black line, you can see that it correlates pretty much very nicely with the loss of fidelity as one would expect. So this population should be ideally zero, but during the process, there are these kinks that you can see here. It's not exactly zero. It has some kind of values which are due to the fact that the process is not adiabatic. And you can see that this is nicely reflected in the value of this average of the angular momentum as well. So we believe that this angular momentum average then could serve as a very nice measure of the imperfection of this process, because it really shows that when this jy is non-zero, there is some kind of population transfer on the first excited state, which shouldn't happen in the ideal case. We can do the same analysis for the two-photon pulse with some kind of detuning delta. We can change the detuning, and what we see is that this population, this error population of the state 1, gets smaller and smaller as the detuning decreases, as the detuning increases, which is what we expect, because the more detuned the process is, the better this approximation of a two-photon process holds. The same thing happens here. This is reflected in the fact that the averages of the angular momentum take a smaller and smaller value as delta increases, as you can see here during the process. So we can nicely characterize now, in principle, all the processes that we have in this problem based on the Majorana representation. Yeah, and we did further analysis. For instance, with the two-photon pulse, we should try to understand how to correct it, because if we don't correct for the AC Stark shift, it will not go to very nicely to the South Pole. But if we do corrections with the AC Stark shift, and that, as Shruti was mentioning yesterday, is done by using dynamically controlled phase, then it goes better to closer to the place where it should go, which is the South Pole. All right, so we then have indeed this polynomial representation. You can see here a nice movie which shows exactly how the state evolves from the North Pole to the South Pole, and it finally reaches values pretty close to where it should be overall. But one thing that I would like to show is that this counter-adiabatic condition can be also derived in the Majorana representation in the following way. So we can write these two Hamiltonians, the stirrup and the superadiabatic stirrup, really like polynomials, like differential polynomials, like of this type, this one and this one. And one can show that in order that the Schrödinger equation to be satisfied in this polynomial representation, then from these two polynomials, one should have the condition that omega 02 is twice theta dot, where theta is this one here. It really can be shown. So you can really derive everything, not in the usual Hilbert representation, but in the Majorana polynomial representation, including this counter-diabatic correction. Okay, so this is what we have seen, that indeed the state would evolve like this. It has some imperfections here that can be corrected by dynamical phases, but it works in principle. So starting from this initial state, there will be these two Majorana stars evolving, going to the South Pole of the sphere. And we can give a thorough characterization in time domain of this process. So we look at the distance between the stars, of the spherical distance, this angle eta that you have seen between the stars. And you can see that in the case of the superadiabatic stirrup, it goes very nicely as we want to go. So starting from 0, going back to 0. But for the case of the two-photon process, it will not achieve perfect transfer, and also for the stirrup process itself, it will not achieve the perfect transfer. It goes back to some non-zero value of this angle, of this distance eta. And pretty much the same thing happens here if we look at the angular momentum. So SAS stirrup clearly performs better than the stirrup, and yeah, also this angular momentum goes to the spot where it should go here in this figure. And then also the fidelity has pretty much the expected behavior. So in the case of the stirrup, the final fidelity, you see it's not 1. But in the case of the superadiabatic stirrup, the final fidelity is approaching the ideal value 1, as it should be. We can plot also the concurrence. Remember that in this representation of symmetrized 2 qubits, we can define the concurrence between the qubits. And the same story goes in the case of the stirrup. The concurrence, instead of going to 0 at the end of the process as it should, it doesn't. But for the superadiabatic stirrup, it pretty much goes to the value 0. Now, another thing that we did is that we introduced the representation also for mixed states. This is important because for mixed states, mixed states is something that naturally appear in experiment because we have finite coherence. And so we were wondering how to represent this kind of the processes. So it works like this. We take the density matrix and we do the spectral representation of the density matrix. And we find some of these eigenvalues lambda i's. And if the decoherence is not too high, we will find that one of these eigenvalues is larger than the other two. And like we are interested mostly in, of course, having processes that don't have decoherence or don't have much coherence. And so the dominant value of this lambda I will show us, in some sense, will give some information about how good is the process, but also the other smaller values will count the errors, so to speak, will give an indication of what are the errors that produce mixedness in the system. So we can, and then we can represent each of these chi's here in the Majorana representation as pure states, as we have seen before. And pretty much they look like this. So we have one of the lambdas like this one, and the other two lambdas, they have a peculiar shape when represented in the Majorana picture. And of course, we can also represent, because it's our mixed states, we can represent the trace of rho squared here. And you can see how the lambdas for these particular figures, how the lambdas, they look like in time domain. So this dominant lambda D is called here is this red one. And then there are two smaller lambdas that have much smaller values, which are called lambda E and lambda F. Okay, then what we can do alternatively, this is an alternative method to characterizing this process, is that we can do process tomography, and we understand pretty much now quite well how this can be done. Should use all these Gell-Mann matrices from lambda 1 to lambda 8, and plus the identity operator. And we can find the process matrices chi's, which are plotted here. All the elements are plotted here. So there are 9 of these 9 times 9 matrices. And we can characterize the process further by introducing the fidelities and this kind of distance measure between these matrices chi of 0 and chi of D. D means it has the coherence. Different values of decoherence are here. So D1 is one decoherence value, and D2 is another decoherence value, which is stronger than D1. And 0 here means that it has no decoherence. So we can characterize all these quantities here, all these fidelities and distances between the states for the stirrup and the SAS stirrup and the 2-photon process. So there's a full characterization in terms of process tomography, which is the standard characterization. but you see how much complicated it is when compared to the Majorana picture. It's a very comprehensive, I would say, characterization, but it requires estimating all these 81 basically matrix elements that appear in this kind of histograms. All right, so this brings me to my endpoint. So what I would like to convince you, have liked to convince you in this talk is that Majorana representation can bring a very nice addition to how we understand these adiabatic and superadiabatic processes in Q-treats. So it's a geometric representation that that allows us to show on the block sphere the evolution of the state as we apply pretty much any process. And it's a very simple, relatively simple representation that amounts to solving a very simple finding the roots of a second order polynomial, which is of course very simple to do. So we think that it could find applications in everything that has to do with three-level systems. Thank you. That's pretty much it.
All right. Thank you very much for the nice talk. And the floor is open for questions. If you have questions, please raise your hands or unmute yourself and you may ask your question.
Hi, Soren.
Hi.
Hey, so thank you for the very nice talk. So I was just wondering whether you have tried to do to incorporate quantum speed limits into this analysis, because one of the kind of interesting directions with respect to doing superadiabatics has been to try and do superadiabatics at the speed limit. And
Yeah.
so I'm wondering if this is something that has come up in your discussion.
Right. So here in this
Okay.
plots, it's
I missed
exactly
this.
what. Yeah, it's exactly what we have tried to do. Maybe I should. So you can define the speed limit in a relative, perhaps naive way. But what we are using is the definition, kind of standard definition that is during the literature to Bhattacharya, and it comes out like this. So it's approximately, in our case, you can define it based on that definition, and it comes out as being roughly 2 divided by the maximum power or Rabi frequency between 0 and 2 that we put in the system. And compared to what we can achieve here, so this is 15 nanoseconds here, this is the maximum we could achieve. And this maximum speed limit that is in principle achievable in this limit is about 7 nanoseconds. So we are by a factor of 2 and something above the speed limit in the experiment.
Oh, I see. Very interesting. Thank you.
Vikash, please ask your question.
Hello, Professor. So in the beginning of your slides, you mentioned this gauge invariant phase.
Yeah.
Right? And you measure. So how do you measure it in a 3-level system?
Yeah, so here is the measurement, actually. What you see here is the result of the measurement. So what we do here is that, for instance, we keep, you see there are 3 phases here, 0, 1, 1, 2, and this phi 2 phi here. And for instance, we can keep either one of these, either 2 of these 2 phases fixed and vary the other one. And so that's pretty much what we can do in order to test this equation. And when we do that, we see this kind of pattern that appears. Mm-hmm. And these are simply probabilities or populations that are transferred to the state. So let's imagine that we keep, we take phi 1, 2 equals to phi 0, 1 equals to 0. So we are here, and then we vary this phi here, we move along this vertical axis. So what we see is that the probability, sometimes there is transfer, sometimes there is no transfer when it's dark here, then transfer again, and so on and so on. And we see that this happens with periodicity given exactly by this factor of 2 that appears here. So we do this on this axis, and then we can do this on the same on this axis as well, and on this axis as well, and also in the in these planes. So that's the way to verify this kind of equation. We see that the population which is transferred depends only of this value of this gauge invariant phase.
Yeah, I mean, I don't understand how the population is related to the phase.
Okay, because the population is related to the phase in the following way. So we have this Hamiltonian here, yeah?
Mm-hmm.
The total Hamiltonian is this guy plus this guy. So we have the stirrup Hamiltonian plus the counter drive Hamiltonian. These Hamiltonians have phases 0, 1, 1, 2, and 2, 0, yeah? Which are the phases that we have seen before. And so we can, in principle, evolve the system. We can make a, let's say, you can simulate the system with this Hamiltonian plus this Hamiltonian. And you can calculate the population at the final time based on the phases that appear here. Yeah. So depending on which values I will put here on the three phases, I will get different populations that are transferred. And now the thing that I am emphasizing is that actually what the population transfer doesn't depend on each of these two phases it depends on it depends on the sum of these two phases. You cannot eliminate all the three phases at the same time from the equations. You must keep their sum. That's the important thing, and that creates this kind of gauge type of phenomenon.
Okay, thank you.
Mm-hmm.
Sarang, please. Sarang, do you have any questions?
Hello.
Yeah.
Hello, sir. Yeah, sir. I just wanted to know that where else can be the Majorana representation used?
Where else? Majorana representation has been used in many other applications. I would say that you can, for instance, take any Hamiltonian, especially a system. If you think about the many-body Hamiltonian, which people cannot solve, you can take that Hamiltonian and attempt to represent it in the Majorana representation, and hope that by using the polynomials, you can diagonalize the system in an easier way than by using the Hilbert space. So that's one possibility to use it for many body system. Another possibility is to look at what happens when you have complex systems and you don't understand very well how to characterize the entanglement. Then this Majorana picture becomes a constellation of stars on the Majorana sphere. And it turns out that for some interesting situation, you can, the geometry of this constellation gives you some kind of information about the type of entanglement that you have in a system. It's of course a many qubit system typically that we discuss about. So we can generalize it to more than 3-level system for sure. And then you have a characterization of entanglement for a many qubit system, which is of pure geometric nature. This has been done as probably one important direction that aims at visualizing entanglement.
Okay, sir. Thank you.
Mm-hmm.
Dr. Usha?
Hello. Thank you for a wonderful lecture. I wanted to know the dark state when it is reached, population reaches 1 in the dark state. Mm-hmm. So it is going to be something related to entanglement, in which case you have the Majorana spinors being orthogonal, that is in a Bell state.
Yes,
so
that's correct.
Can you have a connection like that?
Yes, exactly. That's absolutely correct. So we, in fact, you are perfectly right. You can see, where was this slide? For instance, here you can see that this is exactly what happens. So the concurrence reaches a maximum at half of the duration of the process, where the system becomes a bell state.
Yeah.
And then
so,
decreases.
but when it is separable, completely separable, or when concurrence is zero, there is
yes.
the other way. So there is a connection between, you would mean to say, the dark state and the entanglement. There is a clear connection.
Yes, exactly. So the dark state in this 2-qubit representation becomes, can be represented, and in the middle of this process, it has a maximum entanglement. It becomes a bell state. While here in the beginning and the end is just state 0 and state 2, so they have no entanglement.
Yeah. And also in the case of the ladder model and the what is V model, will you be able, do you think the similar thing with entanglement happens? That is, you have only shown the lambda model here.
Right, correct. But yeah, so we have shown the lambda model because that's the actually the ladder model we have shown. But whatever, everything that I have said applies to the
V and
to the V and lambda models. It's just irrelevant where you put the states, which one is higher, which one is lower. The couplings is everything here.
Yeah. Thank you.
I also have one question. So when you compare your experiment and theory, the population transfer, so there are some deviations. And I was wondering if it is because of some additional nonlinear effects caused by 2-photon processes. Can you please comment?
Yes. So for instance, here or everywhere else, we the most damaging, I would say, process that we have here is that the appearance of the AC Stark shift. So when you, especially when you operate at high powers to create this kind of 2-photon process, there is inevitably going to be a Stark shift. And also, even in the case of stirrup, there is a Stark shift. So we take some measure to cancel this Stark shift. There is some theory paper that we wrote before on how to do that. It is being done in the experiment. It works, but it's not perfect. So there are these additional nuisances besides the existence of the decoherence, which is another major source of imperfection here.
And what about
we do understand these processes pretty well.
And what about the damage threshold? Is it actually the 2-photon powers you are using? Is it very far from damage threshold, or?
I didn't understand from if it's far from what, from.
Because if we crank up the power too much, there may be some damage, permanent damage in the circuit. No.
No. It's well, if we do some damage to the circuit, we will really see it by. We will not have a qubit if we damage something. It's no. It's really still this type of very much quantum-like effects, like Stark shifts and the existence of decoherence that is produces imperfection. Of course, also the pulses, they are not exactly what we put from our generators, is not exactly what the qubit will see, so they get deformed while they travel through the lines, and you put some pulse which you think it's Gaussian, and what the qubit sees is something a bit different.
Thank you. So let us thank again for the wonderful lecture.
Thank you.
Sandeep has some announcement to make before we proceed to the next talk.
Thank you, KP. So I have just a small announcement. At 1:30 or so, we have the poster session today. The posters have been uploaded. You can access them from the program tab. And with each poster, when you click on the PDF of the poster, you will find the link to the chat room or the video conference room where you can meet the author of the poster. So please do so if you are interested. And this announcement is actually more for the students or participants who have not provided us with the link of the video chat room or the poster. They have not sent us the poster. There are few participants who have not sent us the posters. Please do so before the end of the next talk so that we can upload them and the other participants can come and discuss with you. Okay, that's all. Please continue with the second talk. Thanks.
All right, thanks, Sandeep. So our next talk is by Professor Sai Vijampati. He did his master's from IIT Chennai in 2004, and he did his PhD from LSU 2010. I don't know what this abbreviation stands for.
Louisiana State University, I'm sorry.
Okay, so and then after that he did a couple of postdocs in Boston and CQT Singapore. And currently he is working as assistant professor at IIT Bombay from 2016. He has many research interests in quantum synchronization, quantum thermodynamics, quantum control, and quantum metrology. So Professor Sai, the stage is yours.
Thank you very much. So first of all, I want to thank all of my friends here at IISER Mohali for this kind invitation. This is fantastic. I'd really like to visit all of you in IISER Mohali when all of this is done and dealt with respect to COVID. I also want to just take the opportunity to thank you for allowing me to pop in and out. We've had PhD interviews over the last couple of days, so that's been something that's I've been trying to manage on the side. So with that, let me just begin the talk, and I'll speak slowly so that the poster presenters can quickly make their posters and send them to Sandeep. This is joint work with Guruvamsi Policherla. Let me just try and figure out how to get the, sorry, I'm just trying to get the button that allows, is it the annotate button that I should, yes, and the mouse. So can all of you see my mouse? No, I cannot see my mouse. Sorry, could I ask the organizers, processing, like, what do you see? Do you see the title slide? Because I'm unable to see I'm unable to see my mouse. Ah, okay, so, okay. Now you can see the spotlight as well, right?
Yes.
Okay, thank you very much. Okay, so this is joint work with Guruvamsi Policherla, who's a fantastic undergrad who's just finished with us, and our work is on the archive, so I point you to the reference for all of the details of the talk. So let me begin by actually trying to motivate the problem, and I think once I motivate the problem sufficiently, the solution will kind of make itself available and it'll become hopefully clear. So where to start? I want to present you basically three separate motivations. So as the organizer processing kindly introduced me, I'm interested in quantum control, but I'm also interested in quantum sensors. There's various different points of view that I have to this problem. So I want to share with you a couple of different points of view here. One of them is basically, I think one way to think about the problem that I'm going to discuss today is to kind of think about the hierarchy of computation, basically. How would you build a quantum computer? So if we went out into the real world and started discussing that very seriously, well, of course, you know, for many years, the physics community dominated the discussions on operations on single physical qubits. And slowly but steadily, you know, us and our colleagues in the engineering departments have been trying to climb up this, this little ladder. And so here is fault-tolerant quantum computation, which requires, you know, thousands, if not hundreds of thousands of qubits for us to achieve basically, let's say, implement Shor's algorithm at any level that would be considered impressive. But then there is basically this whole hierarchy here, where at the very bottom of the hierarchy are physical qubits. And the physical qubits, basically, we're used to thinking of them quite often as Hamiltonians. So here is a Hamiltonian for a transmon qubit. And you could ask, for instance, to execute with this kind of a Hamiltonian, you could ask to execute something that's an operation on multiple logical qubits or multiple physical qubits in this case. And if you ask for operations on multiple qubits, then you run into the kinds of problems that Professor Sanders's group considered a couple of years ago. So what they considered is basically three transmons that were coupled to each other, and the first 4 energy levels of each transmon was modeled. And what they were interested in was the computational space, which was just the lower 2 levels of each of these devices. And they were interested in performing an optimized Fredkin gate, basically. So if you take this problem and you approach it from the other side, so if you ask how much time does it take for me to perform a Fredkin gate, if you go ask a computer scientist this question, then you're approaching the problem from top down, basically, essentially somewhat from top down. And here, basically, what they would tell you is they would say, well, consider a universal gate set, because you've done the fault tolerance, you've done everything, now you just have a universal gate set. And with that universal gate set, I can tell you how long it takes, because in terms of the universal gates, you have to decompose the gate that you want. So the Fredkin, for instance, would be decomposed in this particular way. So here is a reference for that. And so what I want to do is draw the tension, but also the collaboration between this digital approach versus analog approaches. And especially in this era that we sit in now, where basically we don't have error correction, we don't have this full-blown error correction, this is quite important. So this is what's highlighted in this slide. So what we have is basically hundreds of qubits, and I'm already exaggerating when I say that, but we have to go all the way over here, basically, between tens of thousands to hundreds of thousands of qubits before we can start doing the kind of the prototypical quantum computing algorithms. So there is this whole gap here, which is basically available to us in the sense that there are these NISQ devices that are being constructed by companies, industry partners, and academic partners. And we as a community have to respond to that by creating algorithms and coming up with ways to exploit them that demonstrate a quantum advantage. So this is something that's the one way to motivate basically the conversation at hand. So so the way to talk about this is to say I have a small number of qubits, maybe it's a few hundred, so your definition of small might vary. You could have noise in those qubits, so you could explicitly demand no error correction. You could also demand what your noise model is in a very specific fashion. And then you could say, well, what can I do with this? And so here is basically a list of things that have been suggested in a recent report. And one of them is quantum chemistry, and the other is these quantum algorithms that I'm going to talk about in a second now, variational algorithms that I'm going to talk about in a second now. So that's the motivation that I, again, want to highlight. And the last motivation that I want to draw your attention to is that what this talk will aim towards is to take us from the conversation the beginning of the conversation, where I'll be talking about trying to estimate ground states and trying to estimate static objects. So this is basically the estimation of the ground state of the hydrogen molecule. I will go from talking about these kinds of things which have been demonstrated in the literature already to trying to do direct quantum chemistry on quantum computers. So how do you quantum control on quantum computers? So how do you do quantum control of chemistry on a quantum computer? So this is a very interesting question for those of us who follow the quantum control literature. So for instance, femtosecond physics has basically been already used to control chemical reactions and so on and so forth. So this kind of space is actually quite rich for some very, very useful applications in the near future. Okay, so that's the motivation of my talk. So with that, I'll actually try and keep this simple. I know that it's a diverse audience, so I'll just keep it simple. And what I'll do is I'll actually start from something that all of us know and share, which is standard variational principles, Ritz variational principles, and introduce through that basically variational quantum algorithms. And as a counterpoint, introduce basically quantum control algorithms then. So this is one way, not the only way, but one way to introduce quantum algorithms, quantum control algorithms. And once I've done that, I'll basically discuss algorithmic primitives for each, basically. And I'll make some conclusions and some remarks about formal things like proctorization and so on and so forth. Okay, so the bottom line of the talk will basically be this thing, some primitives for quantum control algorithms. So this is basically the whole point of the talk. Okay, so with that little introduction, let me just start by taking on the kind of the classic quantum control algorithm that all of us, the classic variation principle that all of us know, which is Ritz variation principle. So here is a Hamiltonian, and I'd like to know the ground state of the Hamiltonian. So this is the helium problem, is kind of the classic textbook example that we all work out. So what you do is you propose a trial wave function with some parameterization, psi of lambda, and then you estimate the energy of this Hamiltonian in this wave function, and then you basically minimize over the set of all parameters that you have lambda. So typically, in the way that it is presented in the textbooks, the Ritz variation principle, this minimization, which is actually a first order variation over this parameterized energy, it takes the form where the estimate looks exactly like this, right? So it doesn't look like we've done much. But indeed, there is actually one more step of the derivation that you go through, and then you arrive at this formula again. So if you're unconvinced by that, then you can try doing Newton-Raphson, for instance, for which the cost function that you're trying to minimize, and then the algorithm that you get, which we all know what the algorithm is, 1 minus f prime by f. The two algorithm, the two are actually distinctly different. So the point I want to make to you is that this is something that we've known for many, many years, from the early days of quantum mechanics. And this is something that recently has caught the attention of this community that's been trying to use and exploit NISQ devices. And the proposal is the following. So the proposal is to use a variational quantum algorithm. And so the variational quantum algorithm has the exact same steps as the Ritz variation principle. So this is the reason why it's called the variational quantum algorithm. And the way it works is the following. So what you do is you prepare a quantum state psi with some parameters lambda. And I'll show you how to parameterize the quantum state in a second, but just assume that you can do this on a quantum computer. You can just load a quantum state with some parameters lambda. And then what you do is you estimate this energy functional E of lambda, and then you send it to a classical computer. And what the classical computer does is it takes this energy E of lambda, and it does, let's say, a gradient walk. So it just does a gradient descent, and it tries to basically tries to go through an update step. I've just written it generically as delta lambda. And then once it does the update, it revises the parameters lambda, and you prepare the state again. And then once you prepare the state again, you go through this loop over and over again, and till you hit basically a stationary value. So this is the fundamental idea, which has been quite successful in the recent past. There's been tons of examples of quantum advantages and algorithms that have been shown to be quite useful. And so what I want to do is, the focus of my talk is not VQAs. The focus of my talk is actually to do the quantum control version of VQAs. So what I want to do is I just want to abstract out the main bits of the discussion so that we can carry them over to our work. So the main bits of the discussion are the following. One is that you have to make a parameterized state, right? So I wrote this psi of lambda. I used a scalar notation, but now I'm explicitly using a vector because I'm going to expand out several lambdas here. So how do I prepare psi of lambda? What does this mean? What did I mean when I said psi of lambda is made on a quantum computer? For instance, what I mean is that there is a product decomposition in terms of fundamental gates, or fundamental Hamiltonian evolution, e to the I minus I lambda k OK. And OK are some Hamiltonian element, whatever you want it to be. And there's many different examples in the literature acting on an initial quantum state, psi naught. Typically, it's taken to be like all ground state or something very simple to make. So once you basically, so here is an example of something that's a hardware efficient implementation. So it's essentially few qubit rotations combined with basically a giant entangling unitary operator in the middle. So there have been examples in the literature where people have tried to basically discuss parameterized state preparation carefully as well. So this is something I just want you to hang on to, because this is something that I need for the discussion that we're making as well. The second is measuring the desired result, right? So once you have this parameterization, this is not enough. You actually have to make this measurement. And this measurement is going to basically be, that's going to be a big story. The third is updating the parameters, right? So what is done typically in variational algorithms is that the estimates are computed on the quantum computer, but all the optimization is done on the classical side. So it's a classical quantum hybrid algorithm. And the quantum, the only job that it does is it just estimates numbers. And then the classical part does all the optimization. So if you have a gradient estimator, a gradient search algorithm running, The gradient search is on a classical computer. Where you need the numbers, you just go ask the quantum computer for the numbers, and it gives you the numbers in terms of measurement results. So what I want to do is I want to focus on this step 2 and step 3, and that will bring us neatly into the kind of little primitives that we will also use in the quantum control literature. Okay. So one kind of famous, now famous algorithm that's used, algorithmic primitive that's used, is what's called a linear combination of unities trick. So what is the linear combination of unities? Suppose I want to estimate some expectation value of some x. And now the operator x, I don't even care if it's not Hermitian. I just take it to be something, some number. And now I want to know the expectation value of x. So in general, it's a complex number. What do I do? What you do is you basically write x in basically a poly decomposition basis. So if you want, that's the simplest way to think about it. So you write your poly basis for the n qubit states that you're sitting in as basically sigma k1 tensor sigma k2 sigma kn, and then k1, all the ki's can take 0, 1, 2, 3, and 0 is the identity operator, so it covers all operators. Then xk simply records basically the information about the matrix X, right? If xk is complex, then, but you don't even need the small xk, you don't need to instantiate it inside a computer, because all you can do is when you make this expectation value, is you can basically just compute psi lambda on basically one of these sigma k's. And these sigma k's are just unitary operators. They're just poly flips on basically a string of gates that are sitting around. So that's the way in which linear combination of unitaries has been used in the literature. So it allows us the freedom to basically just take ourselves off of the of trying to basically implement this Hamilton, this operator X in a complicated fashion. And it simply moves it over to the complexity of implementing the poly decomposition of it. So if there is kind of, if there is an exponential number of terms in the poly decomposition, well, then you'll have to sit there and doing this experiment forever. But otherwise, what you can do is you can compose this estimator by basically this estimation by basically just taking in linear combination x vector k, the expectation value of sigma vector k in the state psi lambda. And that's the way in which you would compose the expectation value, right? So I again want you to hang on to this. LC uses something that I will use as well. And I just want you to just come along with me for that discussion. And the second algorithmic primitive that I want to discuss before I move over to the quantum control side of the conversation is something called a Hadamard test. It's as old as time now. And the Hadamard test, sorry, there should be a reference here by Arthur Eckert and several other people. The Hadamard test is the following. It basically is simply the statement that if you have a control qubit which is in 0 and any quantum state psi, a generic quantum state psi, then if you apply the Hadamard and then a controlled unitary, then you basically, it's a simple algebra. You can work out that you get this 0 psi plus 1 u psi. And then when you apply a Hadamard again, you turn amplitudes to intensities, and then you can measure these intensities. So this 1 plus u psi, 1 minus u psi allows you to calculate the real and imaginary part of u psi u, basically. So that's the way in which the Hadamard test can be used to calculate u psi u, the real and imaginary part of this. So these two tricks have been basically used in combination all over the place. And so if I want to say it basically, again, to bring back this kind of a diagram, well, this is, well, somewhere higher up in this diagram is where we're operating, because we assume that we can do kind of, many gates. And now the question that we're asking is basically, we're asking, can I optimize static quantities? And and VQAs as a kind of whole school of thought is allows you to answer that question. So what I want to do is take this and show you that you can actually extend this to not just a variational principle which minimizes one number, but a variational principle that minimizes a path, right? So that's the rest of the conversation that I'm going to walk you through. Okay, and that actually brings me to quantum control, because for me to show you how variational principles can be used to minimize paths, optimize paths, I have to walk you through the conversation about quantum control, which I will right now. So The story of quantum control. So here's a quick example of actually an optimal pulse sequence that you can get out of quantum control. So the story of quantum control can be succinctly represented in the following fashion. So imagine that I have a quantum state psi 0, and I want to go to a target state, which I have written as a projection operator Q, which is tau tau, right? It can be an arbitrary Hermitian operator Q. And so if I want to go from psi 0 to Q, then what I'm asking is, can you please minimize the distance basically at some given time to the target operator Q, along with some additional constraints. So the additional constraints are things like minimizing fluence, which I'll show you. It's minimizing power, which Sorin was talking about a second ago. It's minimizing the distance to the target state. It's minimizing bandwidth constraints, so on and so forth. All of these kinds of experimental constraints that are very, very relevant to doing real quantum control. What quantum control theory has done thus far is basically constructed the mechanism for us to kind of put all of this into one cost function and then find answers, find optimal pulse sequences. So the pulse sequence that I showed you here is super counterintuitive. In fact, the reason that I put this up is to just remind us that these are not analytically solvable pulse sequences. So it's not a simple sine or cosine wave that I could have arrived at by simply thinking a little bit harder. It's actually something that's the solution to a variational problem, and hence it's actually quite complex. This is all I just wanted to, the reason why I wanted to flash that. Okay. So here is the example again. Let me just show you in one last detail. It's a very famous paper by Zhu and Rabbits. So what they do is they take the Morse potential. So they're basically considering the OH molecule. And what they want to do is they want to control it such that it's at the origin at time t equals 0. And at some finite time t, it's at some place x prime, basically. So the operator that they basically take, the target operator that they want the overlap to be the largest with, is this Gaussian representation of a delta function, basically. And then what they do is they ask for a cost function. So the formal cost function that they have is basically the overlap to the target operator minus basically the fluence. So the fluence is basically the electric field that they apply, squared, integrated over time. And this difference is basically a very, very famous cost function that's often discussed in quantum control theory. Okay, so let me say it more formally. So in a way that is kind of that takes away the details of the Zhu and Rabbits example and puts it in slightly more general terms. So if I have a target state tau, then I can write the formal Krotov cost function J as basically the fidelity to the target state. So I want this to be the largest at time capital T, minus the fluence, and then you can add or you can leave it. It just shows up the moment you do a first order variation. You can add the Schrodinger equation in there. I like to add the Schrodinger equation in there because it points out that there is one more vector here that also shows up in the control theory. And this vector is a vector Lagrange multiplier that enforces the Schrodinger equation at all times. So this is typically called the co-state. So you want to optimize the state psi of t, and the optimization is enforced essentially by this co-state chi of t, right? And so again, what do you do? Like all variational principles, what you do is you seek the first order variation. This is no different than perhaps the example, the undergraduate example that we work out, where we work out the Euler-Lagrange equations, right? So you choose stationary action, and then that produces 3 equations in this case, because the state is linearly independent from the co-state and it's linearly independent from the magnetic field. So you want all 3 of these, basically their first order variations to be 0, so that the cost function's first order variation is 0. So if you demand this, you get 3 equations because you've asked for 3 derivatives. And the 3 equations look like this. Now what I've done is I've played a sleight of hand. I've actually switched out the Euler-Lagrange equation for an iterative Euler-Lagrange equation. So this is a little bit like switching out Schrodinger equation for basically a Hartree-Fock type equation, which has an iteration parameter inside it. And the iteration index k, simply all that you need to take away from this slide is that this is the state variation, co-state variation, and magnetic field variation. So the three equations that I told you existed before. So these 3 equations. The only additional thing that I've done that Krotov did originally was basically solve them in a self-consistent in iterative fashion so that you get a convergent solution. So it just converges to the correct answer, exactly like Hartree-Fock, if you remember that theory. Okay, so so this is what the Krotov algorithm looks like if you actually want to formally write it as a kind of flowchart. So you guess a control field and you just put it in and you run through an entire loop. This is not very relevant, so I'll leave it out. The only thing I want you to take away from this is that you have to update the quantum state. You have to evolve the quantum state. So let me just go back for a second. You have to evolve the quantum state from the initial point psi naught at time t equals 0. You have to evolve the co-state from the final point. So this is just something that's very common to variational principles. And then you have to compose this overlap operator. So these 3 steps you have to do at every point in time, and that's how you evolve the control algorithm. So at every point in time, you just run this algorithm again and again and again. For one iteration, you run it from 0 to t, and that's one iteration, and then you run it again, you run it again, you run it again, and the solution converges to a kind of solution that I showed you before with the Zhu and Rabitz kind of complicated electric field solution. Right. So for open quantum systems, we have done something. So this is a reference for that. So that's not the only optimization algorithm that's available in the literature. So here is another one. This is a very famous one, and I'll just stop with these 2 famous examples. So this is called the grape algorithm, and it's often used in all of the NMR literature and NV centers literature. So it's a very famous algorithm, and basically it relies on directly trying to maximize the fidelity to the final state. So this is just the fidelity to the final state. And you can write the Schrodinger equation I psi dot is H psi. And then if you just basically perform some derivatives and so on and so forth, it's just some simple algebra. Again, you end up with basically a term that looks like a backward propagating solution. So what this is its target state that's pulled up to time t. And this is the initial state that's pulled up to time t. And then you compare the fidelities at that intermediate time step. And that's the way in which at a time step, let's say time step number 4, you can basically, you pull from one side, push from the other side, and you compare the fidelities and you calculate basically the update terms, right? So the math on this is simple, but kind of, I just wanted to flash one thing here, which is the only thing that I want as a motivation for us to go into the next part of the talk. And that is basically the update of this grape algorithm involves basically a term of the following kind. Some quantum state, which is basically evolved from back in time, some quantum state that's evolved from forward in time up to some time t, and then an operator that you have to take the overlap with. So this U is basically the exact same as the controls. I've just changed it from Xi to U because I went from Krotov to Gray. Just to keep them separate from each other so the formulas don't confuse us. This dH by du basically is just whatever operator controls the magnetic field. So let's say I have a mu dot B, it's just the mu operator, the dipole moment operator. So that's what's sitting here basically. So all that I want you to take away from is basically the following thing, which is that there are 4 steps that I have to basically execute. Step number 1 is I have to evolve states forward in time. Step number 2, I have to evaluate state overlaps, right? Because I need the overlap between quantum states. I'll show you where it comes up again. Step number 3, I need transition amplitudes. So I'm calling transition amplitudes things like this, psi operator tau. So right, so this is a transition amplitude. And the 4th is basically if I can get all 3 of these, then I can do the optimization, right? So that leads to the optimization. So let me just add that there are a few more complications. So I've highlighted all the complicated steps here now. So if I think of a generic many-body quantum control problem, then basically evaluating state overlaps is actually quite difficult. Evaluating transition amplitudes is quite difficult. Forward and backward evolution is quite difficult as well. And evolution becomes tedious. So this is the point that I just mentioned. And then tomographic measurements are impractical because if I have basically very, very large system sizes, then you can't do 2 to the power of n number of measurements. Basically, this becomes very impractical, right? So in this context, I want to solve this problem. So this has been solved before. So the solution, of course, is to basically suggest that you move from trying to classically simulate it to doing a quantum simulation. So you go to a quantum simulation space. And so you put the whole thing on some sort of NISC device, on some sort of quantum computer. So here is an example from about 2-3 years ago. The only thing, again, that I want you to take away from here is that the way in which they calculate the fidelity that they then optimize is basically by taking the target state and demanding that the target state actually be a sparse set of operators. It should be expandable in a sparse set of operators. And if it's expandable in a sparse set of operators, then they can compute this trace of psi f times ps by just taking projections onto a particular state ps. So this actually is a hybrid Krotov algorithm that appeared in PRL 3 years ago. And our solution, as I will show you in a second, will do much, much better than this. We can actually accommodate dense target states and bypass tomographic measurements entirely. Okay, so with that, let me present the solution in the last 10 minutes that I have. So the solution basically is two algorithmic primitives that I will basically highlight to you. The first algorithmic primitive is basically something that I will call the overlap estimation algorithm. So the point that I want you to take away is that till now, all of the algorithms that I've described to you, all of the examples that I've described to you, involve calculating two quantities that then you use to optimize. The first is an overlap between two quantum states, some generic state psi and some generic state chi, and you need to take the overlap of them at some time t. So they're both time evolving quantum states. So they're evolving in time, and then you need to take the overlap. So the second is basically you need to take the overlap of psi and chi in some operator mu. So you need to compute what I'm calling a transition amplitude, right? So these two are basically if you can do these two efficiently on a quantum computer, then you can do quantum control on a quantum computer efficiently. And essentially all I will show you for the rest of this talk is basically the two primitive algorithms that we've designed, algorithmic primitives that we've designed to basically get this job done. And I'm calling them algorithmic primitives because with these algorithmic primitives, just like matrix diagonalization is an algorithmic primitive, it goes into all kinds of other algorithms that we use on a daily basis. These two are algorithmic primitives that can be used to design quantum Krotov, can be used to design quantum assisted grape, quantum assisted machine learning algorithms, quantum assisted crab algorithm. All variety of quantum control can be done with this basically. And so that's the reason why I'm calling them algorithmic primitives. Okay, so let me just show you a high level diagram of our algorithm. Our algorithm is quite similar to the other algorithms that exist in the VQA literature, if you know them, but with several crucial differences. One of them is basically that we demand that the target state be available to us that we want to optimize. Now you can say, well, this sounds like a very unreasonable demand. What do you mean that you need the target state that you're going to optimize for? This is not unlike basically many examples from linear optics that that we know, the latest of which was Issue's talk yesterday night, where these GKP states are very hard to produce as 1% probability, but when you produce them, you can mux them and you just have them as an offline resource. So if you give me that offline resource, I can optimize the production of those states. So that's essentially the point I'm trying to make. So we can use an offline resource method to basically optimize very, very inefficient state production methodology. This is, I think, practically very useful for quantum computing design. There is another thing that I also want to mention, which is that there are examples of things like 3D tensor network states that are available to kind of linear optical implementations of quantum computing that are not available, let's say, to trapped ions very easily or superconductors very easily. If you can implement a Hamiltonian in several physical systems and generic Ising models, so on and so forth, we know how to implement them across many different physical platforms. Then what you can do is you can optimize over target states which are available in one physical system, like optics, and you can take the optimal solution to some other physical system. So now, even though you didn't have a method to produce optimal, let's say, complicated cluster states in a particular physical system, you have it because you were able to produce the target states in a different physical system and run the optimization algorithms that I'm going to talk about, right? And so the way to kind of correctly contextualize our work is to think of them as gate compilation techniques. So it's quite akin to basically these efficient decompositions that I showed you before, but it's not efficient decomposition starting with universal gate sets, but it's efficient decomposition starting basically from control theory perspective, basically. Okay, so the primary algorithm, our algorithms will look like the following, which is you give me the state, you give me a Hamiltonian which is encoded as basically a linear combination of unities and the initial state, and what I will do is basically run the quantum processor, and the evolution directly has estimators, has amplitude overlap estimation and transition amplitude estimation algorithms inside them, built into them, that will directly take up the overlap delta xi. So this overlap delta xi that I showed you in the Krotov algorithm, I'll show it to you again. This can be directly computed without any additional tomographic resources. They can accommodate dense states so on and so forth. So if you have convergence, then you basically stop. Otherwise, you just rerun the algorithm. So the classical processing is only doing one thing, which is it's only checking for convergence. That's it, nothing else. Okay. So let me just quickly walk through the rest of the algorithm. So remember what I told you, which is that if you have basically Hadamard tests, then you can basically compute the expectation value of psi, right? So in exactly the same way, it's just a continuation of that discussion. If I give you the quantum state 0 psi plus 1 chi, then you can basically compute the overlaps between psi and chi, basically, right? So you can work it out that this is it just follows from the previous Hadamard testing. So now what I have done is I have translated the problem to the following question, which is how do I construct the superposition of two unknown unities acting on two quantum states. Unknown is kind of qualified, and I'm happy to qualify during the discussion. And so let me show you how it's done. It's a modification of actually a method that came up about 4 years ago by Osmaniak, Grudka, Horodecki, and Wojcik, I guess is the way to say that. And it's basically a very nice paper which tells you how to implement the superposition of two unknown unities. So let me just tell you what happens. What you do is, suppose you want to construct 0 plus 1 over square root 2, phi1 plus phi2 over square root 2, sorry. You have two quantum states, phi1 and phi2, and you want to take a superposition of those two. Then what you do is you start with the quantum state alpha 0 plus beta 1 in a control line. And then you feed alpha phi1 into one line, phi2 into another, and using a controlled swap, you basically execute the circuit. And then if you project onto this p chi, then what happens is that for any chi which has non-zero overlap with phi1 and phi2, I'll come to that in a second. What you get if you project onto p mu and p chi is you get the following state, which is alpha times this overlap phi1 plus beta times this overlap phi2. So what's the trick here? The trick is you simply arrange alpha to be chi phi1 over amplitude chi phi1, and beta to be chi phi2 divided by amplitude chi phi2 times whatever numbers that you want. So what happens is that the amplitudes with the known reference state chi just drop out of the physics, and you just simply get the superposition states that you are interested in. So this is the algorithm in a nutshell. Basically, so what we did was we took this and we modified this to basically add control lines to it and then add control unities to it. So let me show you that. So this is basically what adding the unknown unities looks like. So it's the exact same circuit as before. So you have a phi1, but phi1 is now composed of the initial quantum state psi 0 with an auxiliary target, which is basically an auxiliary control, which is in state 0, 1 tau, and then basically you project onto a state, which I will just leave out of the discussion for now. And then once you project onto the state condition on this projector, what you can then do is you can basically apply a control line, and you can apply the V and the U, the two unities that you want to apply on the two quantum states. So U is a unity that acts on only psi 0, and V is a unity that acts on tau. Right, and so what happens is that when you run this algorithm, so what do you get? You get 0 psi 0 and 1 tau in superposition, and so the control line is built into them, 0 psi 0 and 1 tau. So on the control, a condition on the control, you just apply the unity that you want, and that's the way you can do a time evolved quantum state psi of t in superposition with the time evolved quantum state phi of t. Where the time evolution is encoded into these U's and V's. The very last thing I just have to tell you is so what I have done is I have taken the task and I have converted it into basically adding controls to unities. So this is I've pushed everything out to basically being able to add controls to unities. If I can add controls to unities, I can implement this. If I can implement this, I can implement unknown superpositions. If I can do that, I can estimate the overlaps, right? So this is simple logic. So how do I add controls to unities? This is actually a problem that's been solved before. Again, this is Zhao, Tim Ralph, Jamie O'Brien, I think is in this paper. So several folks basically suggested about 10 years ago already that you can do this very simply by something called an internal swap gate. So what you do is any operator that you want to act, let me show you to you in this diagram. What you do is you basically use polarizing beam splitters to take the control line off of the unitary. So what the polarizing beam splitters combined with this particular gates do is they execute the following gate, which is this what is called the internal swap gate, XA. And what the internal swap gate does is it has a two-level atom, a two-level manifold inside a four-level atom, and when you switch it on, it simply moves the quantum state over to the upper two levels. So anything that acts on the lower two levels just doesn't act on it. So that's the way you can implement controls. So it's just a linear increase, a modest increase in the Hilbert space dimensionality, and you get complete control. So this is a well-known solution. So we adopt the solution. I also want to just mention to you that even though you can't break open basically an existing NISC device, this can be easily engineered into transmon devices because they are already anharmonic oscillators. So they have this frequency selective transitions that are already built into it. So you can basically implement this straight on. The third is basically that the complexity of these additional gates that are required, these polarizing beam splitters in this implementation that are required to basically implement an n-qubit control unitary grow linearly in n. So it's not a complicated. If I gave you a solution, but then it demanded an exponential number of resources, it would be unfair. And I'm happy to report that this is not unfair. Okay. So then with one line, I can tell you what the transition amplitude estimation algorithm is. It's just the overlap estimation algorithm added to a linear combination of unitaries. So if my Hermitian operator mu is decomposable as some coefficient CL times a mu L, then basically I just apply the unitary mu L. Mu L is now a unitary. It's a linear combination of unitaries. So I add the mu L line to this whole circuit, and that's it. That just estimates the transition amplitude as well. So I want to emphasize this because I haven't done it before. I have bypassed tomography completely. So already the very nice paper from 3 years ago, the hybrid quantum control paper, we're doing much better than that because our target states can actually be extremely dense and it would be just fine. Okay. So let's go back to the quantum assisted Krotov algorithm and let's just see how this whole thing works. So the way it would work is that what did I tell you what we had to do? We had to basically evolve psi of t. You would just bypass that by running it on a quantum simulator. You would evolve chi of t. You could bypass that by running it on another quantum simulator, a parallel quantum simulator. And you would bring these two together in this amplitude estimation algorithm or transition amplitude estimation algorithm. So that's where all of the this V and this U are basically just, they will look like this. So they're trotterized implementations of the control unitaries that you want to perform. And then what you would do is once you perform this, you compute basically the overlap term that you want, the magnetic field update term, the control field update term. And this control field update term is directly estimated. And then you basically just directly estimate it, repeat the algorithm n times in terms of the number of measurements. And you just, you compose the delta xi, and then you just update the control field and you run the algorithm again. So that's the way you would just, you would do the whole thing. So let me just conclude, my time is up, by basically saying that the way I wanted to introduce this talk to you today is I wanted to introduce it to you in the context of variational quantum algorithms by basically pointing out that VQAs are basically variations of states and variations of expectation values over parameterized states. Whereas what I am doing is variation of paths, right? What we are doing is variation of paths, and it's related, but it's very different as well. There are two algorithmic primitives that I've presented to you for this path variation problem in quantum control. The quantum assisted quantum control algorithms that I've shown you are two of many examples that we've constructed in the preprint. I invite you to look at them. And the central point I want to make is that we only use qubit measurements. There's nothing more complicated than just qubit measurements that we use. It's useful both to do digital quantum simulation. So just to kind of understand the circuit complexities involved, we did the whole thing in terms of digital quantum simulations, trotterization, and so on and so forth. But you could just, it actually is incredibly good and it works incredibly well if you have an analog quantum simulator. So if you have essentially, let's say a 30 qubit device with Hamiltonian controls, so this, one of the examples of this is the Trimon device that Vijay has in Day4. If you have kind of an n qubit device that you can put in a box and you have Hamiltonian controls over it, then we're very, very happy to optimize those kinds of things and directly estimate basically the optimal pulse sequences directly from the experiment. I just want to highlight again that I think there are tremendous applications in modular gate optimization. So optimizing inside boxes of hardwares which have n qubits inside them, running compiled Grover searches, things of that sort, and also quantum assisted chemistry, basically. So quantum assisted quantum chemistry is something that I think many of us are excited by, and this hopefully provides a contribution in that area. So let me just say again, I'm over time, so I'll stop now. But we've also considered in the preprint trotter and measurement errors, and we've shown that they're kind of favorable for many examples that you care to consider. So thank you very much, and I'm happy to take questions.
Thank you, Professor Sai, for a nice talk. So if there are any questions, please raise your hands. Or you may unmute yourself and ask the question. Yeah, Thomas, please.
Yes, hello. Thank you for giving me the opportunity. Yes, that was a fantastic talk, and I learned a lot. I have to go through all the slides again to really take it in. But one question was, you know, you always go to the so you make the measurements on the quantum computer, but then you go and do the calculations on a classical machine. Do you see a way that one could do this completely on a quantum computer? Because then you would have the states, and you could kind of they might already be updated, and then you could kind of carry on there. Or is it in the nature of the game that you always need to have these numbers in order to do it classically? Basically, the question is, can you do the whole thing on a quantum computer, or is that a disadvantage?
I have to think carefully about it. Let me just tell you the first impressions I have. Any measurement actually requires that you break that quantum line. Basically, you need to extract the. So there may be a clever answer in terms of QND measurements or something like that I haven't thought about. I just honestly haven't thought about that. What I would say is that here is the problem that is in my head. So maybe I share the problem with you instead of giving you a solution. The problem is basically that if I perform qubit measurements, which is all that we require, then all you get at the end of one measurement is a up or a down. You just get a 0 or a 1. And however I extract it, I actually need to do an ensemble number of measurements before I can extract the actual control field update term corresponding to that time step and that iteration. And so as of now, I don't know how to bypass an ensemble measurement and directly loop it into quantum. But this is a very interesting question.
Thanks.
Are there more questions? All right, so if there are no more questions, let us thank the speaker again.
Thank you very much.
Wonderful talk. And now we have actually the poster session, and I would request Sandeep to tell us about the further instructions.
Yeah, so thank you, KP. So now we have the poster session. If you want to see the list of posters and the trailer, you can say, for the posters, please go to the program tab, and you see the poster session there in the timetable. You click on that, you will see all the PDFs of all the posters we have for today. So if you like some poster, you can click on that PDF, and you will see the enlarged version of that poster with the link to the video chat room provided by the presenter. So you will be taken to that Google Meet discussion room where you can directly interact with the presenter of the poster. So this is how we have arranged for this poster session. So please have a look, and if you like, then you can talk to the author of the poster. Thank you. We will see again at 3.